This is Jack Jackson. In the previous video, we introduced the hyperbolic trig functions and computed their derivatives. And now in this section here, this video, we're going to introduce the inverse hyperbolic functions and compute their derivatives. So let's just kind of take them one at a time. First of all, notice that if we take f of x equals sinh of x, that function is an increasing function, which you can see its graph here in green. Okay, and in fact its domain and range are both all real numbers. It's an increasing function, so that makes it a one-to-one function. Another word for a one-to-one function is an injective function. So its inverse, which you get by taking all the ordered pairs and just switching the x and y's, will be also a one-to-one, and in fact even increasing function. And so geometrically, any relation has a inverse function, which you find its graph by reflecting the original graph over the line y equals x. So you can see here in the picture we have the graph of y equals sinh of x, the green graph, and the orange line here is y equals x. And if we reflect the green graph over the orange line, we get the blue graph, which is the function x equals sinh of y, or y equals the inverse sinh or arcsinh of x. So we can tell what that function is. You can see it there. We could graph it by taking the ordered pairs of y equals sinh x and reversing them to get this graph. Okay, so there's the inverse sinh function. Okay, and again, but notice for both of these functions, the domain is all real numbers. Now it turns out that there's another way to write these. Remember, sinh of x is e to the x minus e to the minus x all over 2. And it's written in terms of exponentials. It turns out we can write the hyperbolic inverse hyperbolic sine function in terms of natural logarithms, and let me show you how to do that. So we start with the relationship y equals inverse sinh of x. We want to rewrite this in a different way. Well, that means that x equals sinh of y. That's the definition of an inverse function, and there are no restrictions here because the domain and range are both all reals, and this is a one-to-one function, so this is exactly what we want here. Now, sinh of y, by definition, is e to the y minus e to the negative y over 2. Now, I'm going to multiply both sides of this equation by 2 to get it in this form right here. Now, I'm going to add negative 2x to both sides to get 0 on one side. I'm going to put that term in the middle. And then we're going to multiply both sides of the equation by e to the y, which, of course, e to the y times 0 is still 0, so that doesn't change that. E to the y times e to the y is e to the y squared, or e to the 2y. I'm actually really going to think of it as e to the y squared. Then I've got negative 2x times e to the y, and e to the y times e to the minus y cancel out and make 1, but I've still got my minus, my subtraction here. So this is 0 equals e to the 2y minus 2x times e to the y minus 1. Now I'm going to do a substitution where e to the y is equal to u. So this is u squared minus 2x times u minus 1. So if you look at it that way, you can see that this is just a quadratic equation equal to 0 in the variable u. So I can use the quadratic formula. U equals the opposite of b over 2a plus or minus the square root of b squared minus 4 times a times c over 2a, where a, b, and c are the coefficients of u squared, u, and the constant term, respectively. So a is 1, that goes here, here, and here. B is negative 2x, which goes here and here, and the c only shows up once, which is right there. Now we just got to simplify this a bit. Let's see what we can do here. First of all, in the first part, two negatives cancel. That makes 1. 2 times 1 is 2. The 2's cancel. It to be 1 times x. So ultimately, that first part is just x. Now, negative 2x squared is 4x squared. And all these two negatives here make positive. 4 times 1 times 1, that's positive 4. 2 times 1 is 2. We can factor out of 4 using the distributive property here. And the square root of 4 times parentheses x squared plus 1 is the square root of 4 times the square root of that x squared plus 1. Square root of 4 is just 2. and the 2's cancel here. And so we get u equals x plus or minus the square root of x squared plus 1. But now u is e to the y. So e to the y is x plus or minus the square root of x squared plus 1. Now, it turns out that the only part that really makes sense here is the plus, the only part that gives us any solutions. Because if you put in a negative number here, notice that x squared plus 1 is a little bit bigger than x squared. So the square root of x squared plus 1 is a little bit bigger than x. Okay, and if we take x and we subtract something a little bit bigger than x, or the absolute value is a little bit bigger than the absolute value of x, we subtract that, we're going to get a negative number. And of course, e to the y is a positive number. So the only way this is going to work out is if this is a plus here. Now we can rewrite this as a logarithmic form. The base is the base either place, so this is log base e of this part here is equal to the y. So the y is the logarithm, and the word logarithm means exponent. And so we have solved this so that sinh inverse of x is the natural log of x plus the square root of x squared plus 1. Remember that this is not a power, like just like it's not a power for inverse sine, for example. Now we could actually find, well, first of all, let's check this, I guess. So let's check this with Graphmatica. One way we can check it with Graphmatica, let's see if I can show you that here. So we want to do, so let's graph a couple things. So first of all, if we graph y equals sinh of x, that's built in Graphmatica, so there it is. So now if we change this to x equals sinh of y, let's see if we can get this to fit in the window a little better. So if we do x equals sinh of y, then it's going to reflect over the line y equals x. Now, so you can see that to start with. Now I'm going to get rid of this one. This is our original one, let's make it blue. Okay. Now let's graph the other function that we just came up with. Y equals ln of, what was it? Let's look back and see. X plus square root of x squared plus 1. Parentheses, x plus square root is sqrt in Graphmatica, x squared plus 1, close, close. Now, if we did it right, this should graph over the same thing. We'll see a color change here probably. Yep, there it is. You see it? Okay, rewind that if you need to, but that we saw a color change. So that is the same function. We can also check this on our graphing calculators. There is a sinh inverse of x on a graphing calculator. However, finding it's a little bit interesting. So one way you can find it, really, about the only way you can find it, is to go to the catalog, which is second and 0 down here. And then let's look to the s's, so I can just press the S key, which is right here, and keep going down. And there is a sinh and an inverse sinh actually in here. There may be a way to get them out of a menu, but I'm not sure where it is, if there is one. So there we have inverse sinh. And the other way we can do it is ln of x plus square root of x squared plus 1, or something right at 1 plus x squared. Okay, now if we did that right, when we look at the table should match. And we can also get the calculator to get it to graph for us. Notice there's some positive and negative values and it's matching up all the way. So that's a good check there. Alright, so now we've seen that we can rewrite inverse sinh as a logarithm. Now we can actually find the derivative a couple of different ways. One, we can use the fact that we know the derivative of sinh of x, and we can use our inverse function rule to go through with to work that out. But eventually we're going to have to switch things up get it to simplify. And it's actually going to be easier if we just go ahead and do that right up front. So let's go ahead and switch it up to logarithms and then do the derivative that way. So let's do it. Let's do that rather than our other option. So the derivative of inverse sinh of x is the derivative of the log of x plus square root of x squared plus 1. Well, now we know how to do this. This is log of u, so that's 1 over u, okay, times the derivative of the inside. Now, by the way, I should have put the restriction that this part here must be positive. Okay, so let's keep going. That may or may not show up in the end. Well, actually, x plus the square root of x squared plus 1. I think we'll. Well, let's see. That part there always was positive. Look back at the graph that we looked at here, or we've got it in Graphmatica. Notice that no matter what you put in for x, this thing is defined, so that means you're taking the logarithm of a positive number. So in fact, the domain is all real numbers, so it's not something we actually have to worry about here. Okay, so where are we? Okay, so here we are. Now, so it's 1 over u, 1 over that, times the derivative of the u. So the u is the x plus the square root of x squared plus 1. So this is the sum in the top, so it's a derivative of the two parts added together. The derivative of x is 1. And then we're doing the derivative of, and we're going to think of this as x squared plus 1 to the 1/2. So like w to the 1/2. So the derivative of that is 1/2 w to the negative 1/2 times the derivative of the w. The derivative of the x squared plus 1 is 2x. When we simplify a little bit here, look what happens. The 2 cancels with the 1/2. Okay, and you can think of this x squared plus 1 to the negative 1/2 power as 1 over the square root of x squared plus 1. So you can write it that way. To get rid of this compound fraction, I'm going to multiply by the square root of x squared plus 1 in both the numerator and denominator. I'm just going to leave it factored in the denominator, but in the numerator I distribute. So when you multiply that by 1, it just stays the same. When you multiply this by these two things together here, the square root of all that stuff cancels out, leaving you only an x. But if you look, square root of x squared plus 1 plus x is the same as x plus the square root of x squared plus 1. So these two cancel, leaving you 1 over square root of x squared plus 1, which again is clearly defined for all real numbers because the denominator is never 0, and you're never taking the square root of a negative, because once you square you get at least 0 or bigger, and you add 1, the thing you're taking the square root of is at least 1. So the derivative of the inverse sinh of x actually turns out to be this nice little algebraic function, 1 over the square root of x squared plus 1. And we can see the graph of that. We can do it check it a couple of ways. I didn't check it with the calculator here, but we certainly could. For example, I've got this in here. I can let y2 be the, let's see, numerical derivative of y1 with respect to x, and then x, and let y3 be the derivative that we came up with, 1 divided by square root x squared plus 1. And let's see, let's turn off y1. See a little scrolling later on. And I can look at tables for y2 and y3. Now if we did this right, hopefully these will match, and they do in fact match. So there's another little check for us. Let's see, let me go ahead and show everybody what I had here. Okay. Let's see if I can get all this on one page. Maybe. Let me see. There we go. Okay. So we can also graph them and see that. This is the original in blue, the inverse sinh of x, and the red is its derivative. And look at the characteristics of the graph so we can see that. Notice that the original function is increasing everywhere. First of all, it's defined everywhere, and it's smooth everywhere, so its derivative is defined everywhere. Continuous and smooth. And it is increasing. The original function is increasing, so the derivative is always positive above the x-axis. There's an inflection point at the origin here. So for positive x's, the original function is concave down and the derivative is decreasing. And for negative x's, the original function is concave up, so the derivative is increasing. So at x equals 0, the original function has an inflection point and the derivative has a maximum. Looks like that's at 0, 1. It's exactly at 0, 1. Okay? So you can see that. You can also kind of check it in Graphmatica. Let's see. Y equals 1 divided by square root of x squared plus 1, was it? Was that the right thing? Yes. And then we graph that, but we can also click on this function here, select this function, and there's a find derivative button up here, right here. And oh, it's not going to do it that way. You'd have to do it in terms of the logarithm. Is this the right one? Yeah. We want to do it. There's the logarithm version. And if I select that one and then say derivative, then if you notice, I don't know if you noticed, but that one changed color on us. So that is its derivative. So anyway, there's some there's some checks there for that one. Okay, let's go on. Let's do another one. Okay, so now let's turn attention to inverse tangent, hyperbolic tangent. The inverse hyperbolic tangent is graphed in blue. Notice it's defined only between -1 and 1. Well, let's start with the hyperbolic tangent, the green one. It actually has asymptotes of -1 and 1 horizontally, and so the y's are between -1 and 1, and the domain, the x's, are all reals. So when you do its inverse, you just switch those two things, and so the domain is only between -1 and 1, not including -1 and 1, and the range is all reals. And we can see that graph. So we can also do it in terms of logarithms. Let's look at this one. Y equals the inverse hyperbolic tangent of x. That means x equals hyperbolic tangent of y. X then is e to the y minus e to the minus y over e to the y plus e to the y, e to the minus y. That's the definition of hyperbolic tangent of y. Now I'm going to multiply top and bottom of this fraction by e to the y and distribute. So this is either 2y minus 1 or either 2y plus 1. Then I'm going to multiply both sides of this equation by this denominator here. And that leaves the numerator on the right. On the left, I'm going to go ahead and distribute. So I get x times the e to the 2y plus x times 1, which is, of course, just x. Now I'm going to get the e to the 2y term. I'm going to get the e to the 2y term on this side. So I'm going to subtract 1 e to the 2y, and then I'm going to factor out the e to the 2y, leaving us x minus 1. I'm also going to subtract 1x from minus x from both sides, and so this gets it in this form. Then I'm going to factor out a -1 here, leaving us x plus 1, and then I'm going to divide by x minus 1 to get the e to the 2y by itself. Now I'm going to rewrite this as in logarithm form. The log base e of the right side equals the logarithm, the exponent, which is on the left, 2y, divided by 2, and I'm going to distribute the negative in the bottom here and rewrite this slightly as 1/2 times natural log of 1 plus x over 1 minus x. Okay, Now, by the way, for this to make sense, we must be taking the logarithm of a positive number. And you see, if we're between -1 and 1, then we're in the right place, because between -1 and 1, both of these let's see, if it's between -1 and 1, the numerator and the denominator are both positive. If we're to the left of -1, the denominator's positive, but the numerator is negative. And if we're to the right of 1, the numerator is positive and the denominator is negative. And of course, if x equals 1, then this thing is undefined. Technically, I guess this is still actually defined at x equals 0, but, I mean, not at x equals 0, but at x equal, let's see, at -1. Yeah, it's not going to be defined at x equals -1 either, because the whole thing then would be 0, and the logarithm of 0 is undefined. So strictly between -1 and 1. So that's the domain. That agrees with the picture that we saw. Well, that agrees with it, and we could check it. I'll just show you the calculator here. You can check it yourself. So we do inverse tangent of x. Again, we get that from the catalog on a TI-84, and then here's the other version of it in terms of logarithms. Watch your parentheses there, and we check that out. Of course, the only values you're going to be able to put in here in your table are stuff between -1 and 1, not including -1 and 1, but it does check out that those are the same thing in both cases, in all the cases between there. Now we're going to use the logarithmic form once again to find a derivative. So the derivative of inverse hyperbolic tangent of x, like that, is the derivative of 1/2 natural log of 1 plus x over 1 minus x. So the 1/2 I can bring out front, and it'll be 1/2 times that all the way through. Now I'm going to use a property of logarithms that says logarithm of a over b is logarithm of a minus logarithm of b, which comes from properties of exponents, actually. So I encourage you, if you need to practice some properties of logarithms, to go back to my algebra videos, and I go over that in quite a bit of detail. So the logarithm of 1 plus x, then, we want to take its derivative, and so that's 1 over 1 plus x times the derivative of the 1 plus x. In other words, log of u, the derivative is 1 over u times the derivative of u. Of course, the derivative of 1 plus x is just 1. And so we get 1 over 1 plus x for the first derivative for the term, that term. Now, we get minus, and then we've got the derivative of log of some other letter w. So we get 1 over w times the derivative of w. This time the derivative of w is -1, and the 1 over w is 1 over 1 minus x. So that negative and that negative makes that a positive in the middle. And we need to make the restriction that the 1 plus x has to be positive and the 1 minus x has to be positive. So notice this one says that x is greater than -1, and this one says at the same time x is less than +1. So x has to be in the interval -1 to 1, which is no surprise because our original function x had to be in that same interval. So that's good news there. Just fine. And so anyway, this reduces to this right here. And we're going to get a common denominator by multiplying the first one, top and bottom, by 1 minus x. And the second fraction, multiply the numerator and denominator by 1 plus x. Okay. And then we go ahead and multiply out in the top. Since we got a common denominator, we keep that common denominator and add the numerators. Multiplying out here, this is 1 minus x plus 1 plus x. The x's cancel, and we get 2 in the numerator. Remember this 1/2 that we had way back here? Don't forget it. It comes all the way down, and at this point, it cancels out the 2, leaving us 1 over 1 minus x squared. Now, if you look at this formula right here, it looks like it's defined everywhere except for -1 and 1. But our original function, remember, had to only be defined between -1 and 1. So we absolutely have to put that restriction there. So when we graph this, we need to make sure that we're only graphing the part between -1 and 1, which is this red part right here, the derivative. So here's the arc hyperbolic tangent, or the inverse hyperbolic tangent function here. Notice it's always increasing everywhere it's defined. And so the derivative of it should always be positive, which it is. This function is concave down in the third quadrant for negative x's, and so this one is decreased. The derivative is decreasing for negative x's. For positive x's, the original function is concave up, so the derivative is increasing there. We have an inflection point at the origin where the slope is 1, and there we have the derivative is 1, and that's a minimum value. 0, 1 is a minimum point on the derivative graph. So everything seems to check out. You can check that with your calculator yourself. Now, notice that these were actually one-to-one functions to begin with. So the inverse, let's go back, say, to the original one here. So sinh of x is a one-to-one function, so arcsinh of x is also a one-to-one function. So let's graph, let's do that. Let's go ahead and graph these in Graphmatica too. I think I actually have them here. Let's see. So let's graph. Let's see, what do I have graph? I think that's the derivative. I don't need that anymore. So let's clear everything out. And let's graph y equals hyperbolic tangent of x. Let's type it in again. Y equals tanh of x. There it is. And I've been doing these in green, so do that in green. And the inverse function is, well, one way to write it is x equals hyperbolic tangent of y. And I'll do that one in blue. Maybe I'll zoom in a tad here. Okay, so there is a graph of the hyperbolic tangent and its inverse. Yeah, I already have them both graphed there. So notice that they're both one-to-one functions. I already had this graph. Okay. So there is an issue, though, that comes up when we're doing trig functions. So if we graph y equals cosine of x, for example, we get a wave. It's periodic, and not only is it periodic, that means that it's going to be, one of the consequences is that it's not one-to-one. So it has an inverse relation, but the inverse relation is not a function. But when we say the arc cosine, or the inverse cosine function, it's not truly an inverse of the cosine function. It's an inverse of the cosine function with a smaller domain. And we have the same issue here when we look at cosh of x. So if you graph y equals cosh of x, which is this green graph, and you graph x equals cosh of y, which is its true inverse, you get over here a graph, perfectly fine relation, but this inverse one down here is not a function. So for them both to be functions, they both need to be one-to-one functions. So we're going to tackle this by doing the same technique that we did for the inverse regular trig functions or circular trig functions. We're going to take this original function and throw away half of it, basically, so that we get all the y's included. We're going to try to make it one connected continuous piece if we can. All the y's are included, but they're only going to be included once. Okay, so we're going to end up with fewer x's, half the x's. So in this case, of course, which one part do we want to keep? Well, we're given sort of a choice between positives and negatives. We'll prefer positives, so we'll choose the part from 0 to infinity, this part right here, and then when you reflect that over, you're going to get just the top half of this graph here, and this is what we have here. And so this one here is our original function here. It's y equals cosh x, but only part of it. Only the part where x is greater than or equal to 0. And then the inverse cosh of x is this graph right here, which has positive y's. And of course, x is from 1 to 0, 1 to infinity. And then y's go from 0 to infinity. And so that's going to be what we mean by cosh inverse of x. It's not truly an inverse of cosh of x, but an inverse of a restrictive version. Okay, so we can write this in terms of logarithms again. Y equals inverse cosh of x means x equals cosh of y, but with some restrictions that x is from 1 to infinity and y is between 0 and infinity. So x then is e to the y plus e to the minus y over 2, multiplied by 2 e to the y on both sides. So this is 2x e to the y. Here the 2's cancel, and the e to the y distributes, makes this e to the 2y, and plus, and this e to the y times e to the minus y is 1. Get 0 on one side, like this, by adding negative 2x times e to the y on both sides, and now we use the quadratic formula, where our variable is e to the y. So if you need to do a substitution like u equals e to the y, so this is u squared minus 2x times u plus 1. So this quadratic formula is here. The coefficient of your term in the middle is negative 2x times the variable u minus b over 2a. A is 1, and so forth. There's a quadratic formula. You guys know how to do that. Simplify. The two negatives cancel. The 2's cancel. This first part here is just x. This is 4x squared. This is very similar to the one we did earlier with sinh. This is 4. We can factor a 4 out. Take the square root of that is 2. 2's cancel. And we're down to this point. E to the y equals x plus or minus the square root of x squared plus x squared minus 1. Now, we do have a restriction that x has to be between negative 1 and infinity, and y between 0 and infinity. We had that restriction way up here to begin with. Okay? Now we can take this and rewrite it as logarithms, and in fact this actually works with the positive or the negative, but it turns out that the positive part gives us this blue graph right here, and the minus gives us the reflection of that over the x-axis, which would be the lower half of this. And we're wanting it to be a function, so we're only going to choose the upper half, so we only want the positive, the plus here. So inverse cosh of x is defined then to be, or one way to write it is ln of x plus the square root of x squared minus 1. Okay, and now we're going to take the derivative of inverse cosh of x by doing the derivative of this logarithm part. First we'll check it. So there's the check there in the calculator, and you could check it again by graphing it in Graphmatic or your calculator, but I checked it with the table here. Next, we're going to, and by the way, I needed to put in x's from 1 to infinity, right? Are the only things that would make sense. And there's a single y for the output, which is what we want, because we want it to be a function. Now let's actually find the derivative. So the derivative of inverse cosh of x is the derivative of ln of x plus the square root of x squared minus 1, close parentheses there. So that's derivative of log of u, so that's 1 over u times the derivative of the u. I'm going to rewrite this x squared minus 1 square root of that is x squared minus 1 to the 1/2. Notice that for this to work, our property of derivatives of logarithms says the thing that was inside the logarithm must be positive for this to work, for this to be the proper derivative. Now the derivative here, let's see, the derivative of x is 1. This is like w to the 1/2, so it's 1/2 w to the negative 1/2 times the derivative of w. The derivative of the inside part is 2x. The 2's cancel here, the x goes to the numerator, and then this becomes the square root of x squared minus 1 in the denominator, the 1 plus all that. That whole thing goes to the numerator here, but within that we have another numerator and denominator. Well, that's too many fractions inside of fractions, so let's multiply numerator and denominator by square root of x squared minus 1. I'll just leave it factored out at the bottom, but in the numerator I'll distribute, and so we get the square root here, plus, and then when we distribute here, this cancels, leaving just an x. But if you look, that right there in the numerator is exactly that first factor, so that cancels out, leaving 1 over square root of x squared minus 1. But again, our restriction is that x has to be greater than or equal to 1. For this expression here, as we've seen, for it to be greater than 0, boils down to being x is greater than or equal to 1 for that to work out. Okay, and so there's our expression for the derivative. So the derivative is Cauchy inverse. Derivative of Cauchy inverse of x is 1 over square root of x squared minus 1, x greater than or equal to 1. Notice this formula would make sense for x's anything. Well, for x's less than or equal to less than -1. Actually, this should be. It's actually undefined when x equals 1 as well. See, because you'll be dividing by 0. So let's go ahead and be. This actually has to be strictly greater than. Because we can't be dividing by 0 either. Okay, and we can see that here. When x equals 1, the original function is defined, and it even has a tangent line, but that tangent line is a vertical line, and so the derivative has an asymptote there. The original function, the inverse cosh of x, is increasing everywhere, so the derivative is always positive. The original function is only defined for positive x's, or x is bigger than 1 even, greater than or equal to 1, and the derivative is actually defined only strictly greater than 1 for x. The original function is concave down, so the derivative is decreasing. Like any logarithm, the original function was a logarithm, basically. Logarithms have a tendency to grow and grow and grow, so that they do approach infinity as you go out to the right. So the limit of this is infinity as it goes out to the right, but it grows slower and slower and slower and slower, so the derivative actually has an asymptote of the x-axis here, which you can also see kind of by knowing what we know about functions there. Now, with that going on, I'm not going to go over any more of the details of this stuff, but let's kind of, we have 3 more of these inverse trig functions, and I'm just going to kind of go over the results, and you can kind of go over steps similar to what we just did if you want to work out the details. So if y equals the inverse hyperbolic secant of x, cosecant of x, it can be written as the natural log of 1 over x plus the square root of 1 minus x squared over the absolute value of x. And this is actually defined for any x and y, any x not equal to 0, and of course y turns out to be any y but 0. So the domain's all reals except 0, and the range is all reals except 0. And it turns out that the derivative is similar. So the derivative of that function is the opposite of 1 over the absolute value of x times the square root of x squared plus 1. And if you look at the picture here, you can see those graphed, and they should kind of make sense. You can kind of check some of this on your calculator. But the original graph is in blue. The derivative is in red. Notice the original graph, it's a lot like 1 over x in its basic shape, and so the derivative should be a lot like 1 over x squared in its shape. And you see those basic characteristics. So the original function is decreasing everywhere it's defined, so the derivative is always negative. We see this vertical asymptote on the original function. We see a vertical asymptote on the derivative. Actually, they both have horizontal asymptotes of the x-axis on both the right and left as well. Where the derivative is concave up for positive x's, where the original function is concave up, positive x's, the derivative is increasing. Where the original function is concave down, which is negative x's, the derivative is decreasing. Similarly, hyperbolic secant of x can be rewritten as the natural log of 1 plus the square root of 1 minus x squared over x. This turns out to be defined only between 0 and 1, including 1 but not 0. And this is another one where we had to restrict the domain, because if we just did y equals hyperbolic secant of x, it has y-axis symmetry, and so it's not 1 to 1. And so this is only half of the inverse of the hyperbolic secant function, so that we actually get an actual function here. If you took this graph here and reflected it over the x-axis, you get the other half, which is, we don't want part of this because we want to make it a function. More specifically, a one-to-one function is actually decreasing, so its derivative is always negative, which is down here. So the derivative actually is minus 1 over x times the square root of 1 minus x squared. And again, it's only defined between 0 and 1. This function here may actually, I think this function actually is also defined, normally would be defined some other places as well. I think between -1 and 0, this is also defined normally, but we don't want that part. We want to restrict it to this interval to make it work. Finally, one more. We have the y equals the inverse hyperbolic cotangent of x. It can be rewritten as the natural log of the square root of x plus 1 over x minus 1. This is defined actually, if you look at the graph here, it's defined only between to the left of negative 1 and to the right of positive 1. Clearly it's undefined at 1 and negative 1. If you got 1 here, you're dividing by 0. If you put in negative 1, this works out and you get 0, but the logarithm of 0 is not defined. So we have actually vertical asymptotes of the original function at 1 and negative 1, but the original function is not defined here in between there. So its derivative will not be defined there either. Turns out the derivative is 1 over 1 minus x squared with the restriction that x is between negative infinity and 1, union 1 to infinity, so it does not include this. If we didn't put this restriction, then this function right here would include some graph in the middle here that's not really a derivative of the original function. So you see again, the blue is the original function, red is the derivative. So summarizing, here's what we have. And sometimes because of properties of logarithms, in some cases there are other ways to write these logarithm expressions, but here's at least one way. So y equals the inverse sinh of x is ln of x plus the square root of x squared plus 1. That turns out to be defined and have a domain of all reals and a range of all reals. Y equals inverse cosh of x. It turns out to be the same thing as ln of parentheses x plus the square root of x squared minus 1 close parentheses, and this is actually defined only for x from 0 to infinity and y from 1, and then it turns out y goes from 1 to infinity. And this is one where we need to put that restriction as part of our definition. Okay, and this one down here, y equals inverse hyperbolic tangent of x, turns out to be 1/2 log of 1 plus x over 1 minus x. This is only defined between negative 1 and 1 for x, but y's can take on any value. The inverse hyperbolic cosecant of x is the natural log of 1 over x plus the square root of 1 minus x squared over absolute value of x. This is defined for all real numbers except for 0. The inverse hyperbolic secant of x is the natural log of 1 plus the square root of 1 minus x squared over x. And that's defined from 0 to 1, including 1 but not 0. Turns out y's are all positives and 0. And y equals inverse hyperbolic cotangent of x is the natural log of the square root of x plus 1 over x minus 1. But only this is only defined when x goes from negative infinity to 1, union 1 to infinity. The derivatives then are given by this table. The derivative of sinh inverse of negative x is 1 over square root of x squared plus 1, and that's defined for all reals. We don't really have to state that. That's automatic. The derivative of inverse cosh of x is 1 over square root of x squared minus 1, x greater than 1. We do need to put that restriction because x less than negative 1 would normally be allowed here, and that's not going to be allowed for the answer, so that restriction is important. The derivative of inverse tangent of x, inverse hyperbolic tangent of x, is 1 over 1 minus x squared, and this works between negative 1 and 1, which is kind of already implied by the formula there. The derivative of hyperbolic secant inverse of x is negative 1 over absolute value of x times the square root of x squared plus 1. This is defined everywhere except when x is 0. The derivative of hyperbolic secant inverse of x is minus 1 over x times the square root of 1 minus x squared for x going from 0 to 1. And the derivative of inverse hyperbolic cotangent of x is 1 over 1 minus x squared, and this is defined for x going from negative infinity to 1, union 1 to infinity. One thing's kind of interesting. Look at the formulas for the derivative of inverse hyperbolic tangent and inverse hyperbolic cotangent. It's exactly the same formula, but the domains are almost exactly opposite of each other. A hyperbolic tangent inverse and its derivative are only defined between negative 1 and 1, non-inclusive, and the hyperbolic cotangent inverse and its derivative are defined to the left of 1 and to the right, left of negative 1 and to the right of 1. I should say negative 1 there. And so, of course, neither one of these are defined when x equals -1 or 1. So there is a introduction to inverse hyperbolic functions, and we found the derivatives of, well, we found for at least half of them, and then just went over what they were for the other half.